Hi, everyone. Thanks for coming. Thanks for sticking it out through the last day. So I'm going to be telling you guys about a system that we've been working on at the tail end of the AMP lab and now into the RISE lab to do low latency prediction serving for machine learning applications. And this is joint work with several collaborators. So usually when you hear a systems talk about machine learning, it's about systems for training models. And there's a bunch of great systems work around this process. We have things like TensorFlow, GraphLab, Spark, Atom, Parameter Server, a whole bunch of great systems for training models. And what do you get out after you're done training a model? Well, you get a trained model, which is just a function that takes in some query and produces a decision. So for example, it might take in an image and then produce a label for that image, telling us that there's a cat in this image. Now, once you've trained a model, you want to do something with it. And typically, what people want to do is stick it into applications. They want to use this model so that when unknown queries come in, they can make decisions about it and improve some metric of their application, figure out what content to show or whether to flag a transaction as fraudulent, things like this. And so it's this prediction serving process that I'm going to be focused on today. In particular, I'm going to be talking about prediction serving for interactive applications, applications where we need predictions and need to serve queries on the order of tens of milliseconds. Now, prediction serving raises some new interesting systems challenges. And there's two in particular that I want to highlight today. The first is the need to support low latency, high throughput serving workloads. And the second is the need to support the large and growing ecosystem of machine learning models and frameworks. So let's talk about these for a second. What's challenging about supporting these interactive serving workloads? Well, models are getting more complex. If we look at state-of-the-art computer vision models, these fancy ImageNet models, they can take tens of gigaflops just to compute a single prediction. They're so expensive that people are using specialized hardware, not just for training these models, but for making predictions as well. And because they're getting more complex and they're getting more accurate, applications are relying on them more and more. So they're becoming deployed on the critical path, on the hot serving path, which means that it's crucial to maintain latency service level objectives, even under heavy query workloads. For example, if we take a look at Google Translate, Google's AI team likes to publish papers about their models and their systems. And they wrote a paper last fall that describes among other things, the computation needed to train and serve the Google Translate model. Google Translate translates about 140 billion words a day, which using the numbers in this paper, I calculated means that they need something like 82,000 GPUs running 24/7 to serve this workload. In fact, this is so expensive and such a big part of their serving process that Google invented new hardware. They invented this TPU ASIC just to make prediction serving faster and more power efficient. And this is sort of emblematic of the types of solutions that big companies are using to do prediction serving today. They take their big expensive model and they have one application in mind and they build an ad hoc one-off system specifically for that application. This is how the predictions in things like YouTube and Bing and Netflix and Google Ads and stuff work. These are really high-value models. They put a lot of time and effort into building these applications. But I argue that there's a lot of drawbacks to this approach. First, they're expensive to build and maintain because these are highly specialized systems that require both machine learning expertise and systems expertise. And what you get is a tightly coupled model and application, which means it's difficult to change or update the model as your understanding of the problem evolves. And this is pretty antithetical to the iterative data science process that's commonly used today. And finally, they end up only supporting a single machine learning framework. And the reason this is so problematic is because we don't just have a single application or a single machine learning framework, but we have this rich ecosystem of machine learning models and frameworks that specialize in different aspects of the problem, and that sort of together are what's driving machine learning forward. So why do we have all of these different models and frameworks? Well, part of it is because different frameworks and different models are better for different tasks. You might use TensorFlow in a deep model for something like a machine translation task, but that might not be the right approach for fraud detection. So we have lots of different applications that people are using machine learning for, and we have lots of systems to support these different types of applications. But even beyond that, we might have multiple frameworks, or might want to use multiple frameworks for a single application as we try and specialize and improve accuracy by focusing on different parts of the problem. And so pretty quickly, we end up with this huge mess. We have this many-to-many dependency between frameworks and applications, and no good way to serve them. This is challenging because fundamentally these are machine learning training frameworks. They're built to train models, and they don't really consider the serving context, which means that they're difficult to deploy and brittle to manage. That's why these big companies spend so much time building one-off systems. And also, they have varying physical resource requirements that are really crucial to satisfy in order to meet the performance demands of these workloads. So for most companies, which can't afford to build these new serving systems, these one-off systems, they're forced to use existing tools. And so the most common approach here is to extend the batch analytics process so that after they've trained a model, they then pre-materialize, they pre-score all of the possible queries that they might need. They can then store these pre-materialized predictions in a data store, and then at serving time, they can just look up the pre-materialized predictions, and they can do this at low latency. So they can meet the performance demands. But there's a bunch of drawbacks to this approach as well. The biggest one is that it requires the full set of queries ahead of time, which means that your applications are reduced or are limited to operating with small and bounded input domains. No machine translation here. You end up wasting a lot of computation and space by rendering and storing unneeded predictions, and these predictions are costly to update because you end up rerunning these big batch jobs. So rather than compromising, we built Clipper to address both of these challenges simultaneously. So how do we do this? Well, we simplify deployment by using a layered architecture that separates the different concerns in the serving system. And as a result, we can serve many models across machine learning frameworks concurrently. And then we use classic systems techniques like caching and batching and scale out to get the performance that we need for these interactive serving applications on top of these machine learning models. Clipper is a serving system that interposes between the applications and the models. We serve each model in its own container. And by abstracting away the model, we can use general purpose systems techniques to get performance out of this wide variety of models. So internally, Clipper is composed of a few layers. There's the model abstraction layer, which is what provides a common interface to models while bounding latency and maximizing throughput. And then because you can deploy many models into Clipper at the same time, we also have a model selection layer, which is what allows applications to choose which of these models they want to use to make predictions with at serving time, and even combine predictions from different models. The behavior of the model selection layer is governed by a selection policy, and we use caching and batching to get performance out of the model abstraction layer. We wrote Clipper in Rust. It's about 5,000 lines of Rust for the core system. And then we also wrote our own lightweight RPC framework, which is a combination of Python, Rust, and C++. So now I want to dig into some of the details of the system, starting at the bottom. What are these model containers? So fundamentally, these model containers are a way to provide a common interface to this wide variety of models trained in different frameworks in order to simplify the deployment. And the key here is that by having each model running in its own container, we can evaluate these models using the original code and systems that was used to train the models. Basically, this works by having model developers, once they've trained a model, implement a simple model API. I'm going to show an example of what this looks like in Python. They implement an initialization method. This is how you load the model, because we're taking pre-trained models. And this usually looks like loading some serialized form of the model from persistent storage and deserializing it. Once they have the loaded, trained model running in the container, they just specify how to make predictions with it. Given some inputs, how do you make predictions? Once they've implemented, and because this API, this interface is fairly lightweight, we can implement it in many different languages, Python, Java, C++, R, so on, which means that our model developers can use the native APIs of the machine learning tools that they're already using to deploy their models into a production serving system. Once they've implemented the model container, it gets packaged along with any dependencies into a Docker container, which then communicates with Clipper over this lightweight RPC system that we wrote. Because all the models are running in their own containers, we can have many models deployed at once, and they don't really have to know anything about each other in order to be deployed. But this model container API actually goes beyond just simplifying deployment. We get some performance benefits out of it as well. By running models in separate processes, we get resource isolation. In particular, we get process isolation. And that's actually really important because a lot of these machine learning frameworks that are getting state-of-the-art results on these hard prediction tasks are sort of alpha-level software. They have seg faults, they crash sometimes, and by running them in separate containers, we prevent our processes from thrashing each other, clobbering each other. It also provides a really nice mechanism for scale-out. Some of these models are really computation intensive, as I mentioned. And so if we need higher throughput from a particular model, we can just replicate that model's container, say across a serving cluster, and get nice horizontal scaling. But this by itself actually isn't sufficient to address the performance demands of these interactive applications. And the big problem here is that we have machine learning frameworks, the code that's running the models, that are optimized for batch processing, not for low latency serving. So what Clipper does is we transform these point prediction queries into mini batches in order to improve throughput and more closely match the workload assumptions of these frameworks. There's a few reasons why we actually have batchy or bursty workloads. We have often single page loads generate multiple queries, so we get this sort of bursty pattern where it makes sense to evaluate all these predictions in the same batch. These frameworks are often optimized to take advantage of hardware parallelism or parallel math libraries like BLOS. And then finally, batching also helps us amortize some of the system overheads from this decoupled architecture that we've adopted. But we're faced with a new problem, which is how to batch. What's the optimal batch size? And as it turns out, this depends on the hardware configuration, what hardware is this model running on, the model and framework, what computation is it actually doing, as well as the system load. So in order to address this, we introduce an adaptive batching mechanism, which allows applications to adaptively trade off latency and throughput based on the needs of the application. We use an additive increase, multiplicative decrease scheme. So we increase the batch size until the latency objective, this is an application parameter that the user provides, is exceeded. And then, once it's exceeded, we decrease the batch size by some small fraction. It turns out that this really simple mechanism is actually highly effective and works on a wide variety of models and frameworks. So what does this look like? Well, we first ran this on a TensorFlow convolutional network running on a GPU. This is a pretty small network. I think it's a 4-layer network, but it is a deep network and it is running on a GPU. And we see that, unsurprisingly, as we increase the batch size, our throughput goes up with sort of diminishing returns. So if all we cared about was maximizing throughput, we would want to maximize batch size here. But we have this latency constraint as well. We need to be latency aware when we're batching. And in particular, we need to make sure that we don't exceed the latency deadline that the application has said has given to us. So as the batch size increases, throughput and P99 latency increases. We care a lot about tail latencies in Clipper because that's sort of the performance metric that these applications care about. And so we'll maximize the batch size to improve throughput until the latency deadline is exceeded, and then we'll cut it off there. So in this case, we'll use a batch size of 200. But Clipper is designed to serve lots of models, lots of frameworks. So we want to do a slightly larger scale experiment to see how well this worked across models. We trained several models using a few different frameworks, and first measured their throughput without batching. As we can see, we're actually getting fairly abysmal performance, particularly for some of these linear models, which are doing fairly lightweight computations. When we add adaptive batching, we get pretty significant throughput improvements by over an order of magnitude in almost all cases. And we also see that this latency-aware batching mechanism is able to effectively contain the latencies to this 20 millisecond deadline that we set in this experiment. And if we look at the actual batch sizes that are found for each of these models, we see that they vary somewhat widely, but they're almost all significantly larger than 1, indicating that these batch sizes are fairly large. Now, it's a fair critique to say that all this stuff that I talked about so far is just a way to get away with some of the overheads of this decoupled architecture. But what if we compare it to a more tightly integrated, a more monolithic approach? So there's one system out there that is fairly general, that takes this monolithic approach. So we compared to Tensorflow Serving. This is a serving system out of Google. It's designed to serve mostly TensorFlow models, so it gives up a lot of the generality that Clipper gets with this decoupled architecture. And we think it's a nice comparison point to understand the overheads of this more layered architecture. So we have more results in the paper, but I'm going to show you one experiment that we did. We trained AlexNet. This is an 8-layer convolutional network on the CIFAR10 dataset, and compared so we're serving the exact same model in TensorFlow Serving and in Clipper, and we compared the throughput and latency. And what we see is that Clipper and TensorFlow Serving get essentially exactly the same throughput and exactly the same latency. And basically, what this is showing is that the overhead, or that the complexity of these predictions, these models are so complex that it's by far the dominant cost in prediction serving, and that Clipper is able to effectively hide or amortize the rest of the system overheads and get the same performance as this monolithic system design of TensorFlow Serving, while still preserving the generality and the flexibility of this decoupled architecture. We think that this is a fairly strong argument for our architecture and the generality that we provide. So this is an example. So this is sort of how the model abstraction layer works. This is how we serve models and how we get performance. Now I want to briefly talk about this model selection layer that I mentioned. And this is a way to take advantage of the fact that we can have multiple models deployed in Clipper, and we can actually combine predictions from these models to improve application accuracy or robustness. So why would you have multiple models per application? At first glance, that sounds like kind of a silly idea. But it turns out that in practice, this is fairly common. For one, it's pretty common in machine learning applications to periodically retrain your models as new training data is gathered in an attempt to improve application accuracy. And then also data scientists are constantly experimenting with new models, new frameworks, new features as the state of the art advances. So, for example, one way that we take advantage of having multiple models is using them to estimate confidence. If we have some image that these models are making a prediction about, and they all agree, then it's likely that's probably the right prediction, it's probably the right label. And we can communicate that certainty, that confidence to the application. On the other hand, we might have a more difficult query, which leads to some disagreement between these models. Now, Clipper will still make a prediction, but we'll be able to communicate that uncertainty. We'll be able to communicate that uncertainty to the application, which may choose to take some sort of default action or a safer action by knowing that this prediction was somewhat uncertain. We actually measured this. We have some experiments in the paper, and measured this for some ImageNet models. And basically, we found that by using this confidence estimation, we're able to partition our query workload into a large percentage of queries that we're very confident about and actually get higher prediction accuracy on, and then a small set of queries that we're very uncertain about. Clipper supports other types of selection policies, like using multi-arm bandit algorithms, doing online personalization by figuring out which models work better for which users, and there's details in the paper. So to wrap up, we think that prediction serving is an important and it's a challenging area for systems research, and that it should be a focus of machine learning systems research going forward. We need to support low latency, high throughput serving workloads, serve large and growing ecosystem of machine learning frameworks. We think that Clipper is a good first step towards addressing these challenges. We simplify deployment through our layered architecture. We can serve multiple models across machine learning frameworks and combine predictions between these frameworks to improve accuracy and estimate confidence and robustness. And we employ classic systems techniques to meet the prediction-serving performance needs of these interactive low-latency applications. Finally, we're going beyond an academic prototype. We're building Clipper as a real open-source system. We're preparing for our first release of the system next month, but the code's already up on GitHub, and there's a tutorial and some documentation if you want to check it out. Thank you very much. And I think I have time for some questions.
Yeah, let's thank Dan. Yeah, we have time for a couple of questions.
Yeah, just a quick one, Rick Farrow. So what's your intuition as why batching improves performance? Are you amortizing startup cost?
No. So actually, we eliminate any startup costs by basically pre-warming the model. We preload the model.
Sure.
It's more
when you init.
It's more the fact that predictions, for the most part, are embarrassingly parallel, and a lot of these models have some way to take advantage of that parallelism in different ways. One of the big ones is there's a lot of matrix algebra in these applications, and a lot of them are built with BLOS. That's a big one.
Okay, thanks.
Hi, I'm Amar from MSR. Definitely seems like a very useful system. This is a simple question from the application's perspective. Can you give us an idea of, I've seen batching being used in training quite a bit, right? But this is for inference, effectively. And you have this adaptive batching scheme. Can you give us examples of applications where, if latency is of consideration, you can still have large batch sizes? So for example, in your graph, you had like hundreds of, input items in a batch, right? So can you just give us some examples of that as to when can so many items be batched in an inference task?
Are you asking about when you have so many items available to batch in a single inference pass at the same time?
Yes.
Good. So basically, if you have a big serving application that has thousands or tens of thousands or millions of concurrent users, then you have lots of concurrent requests that are all arriving at the same time, and so we can batch requests basically across users or across sessions into a single batch. Does that make sense?
If you had multiple cars, right, in different cities, they would somehow still be feeding into the same inference system? Is that?
So to be clear, I wouldn't use this in the real-time control loops of a self-driving car.
Okay.
You want everything on board.
Right.
You don't want to deal with going over the network. Think more about web serving applications, things like that, where Google or Amazon has millions of outstanding requests at the same time.
Okay.
Marco from Camps. So this is very, very interesting work and was fantastic presentations, and thank you. So I have one observation, which is the techniques that you use at the system level, they appear to be pretty regular, however. And I wonder if this is a bit, the result of the fact that the frameworks that people are using, as you said, are still a bit, alpha, in the sense that we're still figuring out, what are the right ways to create frameworks for machine learning, and much of the attention of the community is more on the learning performance rather than the evaluation of the models. So if you were to take it a step back and think about on a more fundamental level, if you wanted to tackle the problem head on, what would you change on a fundamental level for the model evaluation? Would you consider different type of hardware architectures? Would you consider different type of distributed systems, and so on?
That's a great question. So if I understand correctly, you're asking, we sort of limited ourselves to this very black box abstraction of these models. If we were to open up that abstraction, what changes would we make to improve performance? That's a really, really interesting question. I have a ton of ideas. A couple ideas. So I think that there's less pure systems answers to this. I think they require the cooperation of people building models. But a couple things. One is to provide, when you're training a model, it might make sense to provide models that have different latency and accuracy trade-offs to provide sort of a more smooth, graceful degradation, depending on your workload. There's already interesting work on using lower precision inputs at serving time to improve performance, to improve throughput. That's how the TPU works. There's work on trying to distill like these massive neural network ensembles into smaller models that recover essentially the same accuracy in order to lower the computational footprint. I'm not convinced that this is beyond hardware acceleration, that this is a problem that a pure systems approach is going to be able to solve. But I think that an understanding of how these systems work is going to be integral in solving these problems.
Thank you.
Let's thank Dan.